Okay, I'm going to talk about. Oh, I should put this on because people can't hear at the back. I think. How about that? Is that? Oh, no, it's not on. Okay, how about that? You want to? Are you controlling the sound again? And okay, I'm going to talk about machine learning and entanglement. What this is for quantum magnets. So I'm going to kind of talk about some machine learning first, and then look at some quantum systems a bit later. So this work is supported by the the MERSEC that we have, but also the quantum stuff is supported by the Quantum Science Center. Key people in the who have contributed are Alan Schrader and Lee at Los Alamos National Lab, also Joel Moore's group, Tianran Chen, who's been doing great work with AI at University of Tennessee. Pontus Laurel, who's moved to University of Missouri, and Christian Batista and his group as well. So many people have been involved in this work. But you know, how many people here actually are experimentalists, or is nearly everyone in theory? I know Igor said yeah. So yeah, so great. Okay, so so actually there's in a way, there's a really interesting thing going on in the experiment, not for all aspects of experiment, but with the changes in technology that are going on, our ability to kind of collect data is, you know, improving actually beyond exponential. I mean, we're going beyond Moore's law actually with information processing and data collection as well. And one thing I'd like to point out is a lot of experimental techniques, particularly with scattering, that we have are in fact computationally limited. There's far more information is collectible than we are even close to using. So advances in computation and data actually can have transformative effects on the way that experiment works and the modalities for it. And one thing that I would say is that I think we're actually approaching a massive transition with certain aspects of experimental science, which is, at least for condensed matter, which is to go from what's been a hypothesis-driven approach or multiple measurements into one which is much more about silicon.
Yeah, it's a moth.
That was kind of animal that ran.
Yeah.
Okay, so they're actually changing an era, another era potentially, where we have data. We have loads of data, and our ability to kind of make sense of it is going to be a different modality where we're going to do harvesting and collect lots of information, and then it's going to be a matter of actually using tools to make sense of it later. So the question becomes, you know, what's the nature of kind of completeness of that data? Is it a well-posed problem or not? In other words, is enough data there? If you have the means, could you solve it? There's a kind of challenge that we have in condensed matter. This is actually ice. So Roderick's there. This is the ice data that I'm going to show a bit later on. But essentially, machine learning comes in a massive way because this is a single data set. It's 1,200 Brillouin zones of data with a resolution of 0.01 reciprocal lattice units in each of the 3 dimensions in that. And it's not a periodic system. So all that information matters, and it's got full energy information on that. In other words, the voxel density in this is 10 to the 11 in this data. So that's astronomical levels of data and fidelity actually in existing instruments. And we're going well beyond that as well. So can we mine it and actually make sense of it? Because you can't even treat this kind of data in conventional ways anymore. It becomes too difficult. But that's the prospects, is that if we can start handling this kind of level of complexity, then we're able to discover things and make advances. Now, you don't have to care about that level of data information. So that's way more information than would be the kind of parameters in any model, right? So that's far more information in a way than you need, but it's all encoded in a nonlinear way, a way you can't really access. You can't back transform this data in a simple way. Neutrons is a kind of power spectrum. It's also got all these backgrounds in it. So you can't do some kind of Fourier transform to make sense of it. So you actually have to process this essentially with a model. And there's kind of halfway house to doing it. And in a way, we can kind of take inspiration from, Tesla recently got rid of 300,000 lines of code, and instead they just train parts of their driving using just data instead. So, the kind of neural networks like the internal combustion engine, right? Instead of a horse and you have to train the horse and all the rest of it, you have an engine that you just put fuel in, our fuel is data, and then the thing actually kind of learns and it does it. So if you can get a good setup in a neural network that's well suited to the problem, and you can get training data, either experimental data or you generate synthetic data, we generate synthetic data, then you can translate these massive data sets into the essence, the ability to extract models. And you can do that. What we did was we realized that, in fact, autoencoders are really well built are really well matching for scattering problems generally. And in fact, you're going to have to put huge numbers of pixels into these, but typically they're going to compress, even training over vast numbers of, let's say, spin systems with lots of different lattices, lots of different couplings. We want to look at the structure and the dynamics and train over that. The compression level is going to be really small. It'll be something like 30 neurons is sufficient. And that's what people are finding with lots of different applications. These are starting to get widely used in neutron science at the moment. And we're typically finding you don't need that many neurons to actually encode, really large numbers of models that you train on. Okay, so actually we have parallels. If you look at something like DALL-E or whatever, then it can kind of reconstruct an image of this room because it's basically taken loads of images of things and it's just compressed it right down to a very small essential thing. And then you're going to go through some generative process to make something up. So even though there's astronomical number of atoms in that room, there's not an astronomical amount of meaningful information in that room. So that's the kind of thinking that was behind the basic schemes. We worked these things out 5 years ago or whatever, but it's taken a long time to start to realize how do we connect it in and use these in practical ways. So essentially, when you have neural networks trained and you train them over lots of modeling. So what you do is, in this case, with models, this is diffuse scattering. So this is a kind of diffraction, but for disordered materials. We feed it through, you go through the training process, you train the neural network, and then you can put data straight into these things. They'll take all the backgrounds and the difficult stuff that takes students years to do, and then you can automate the processes. You can put these in and you steer beamlines and all the rest of it. In other words, there's ways that you can have almost automated modeling and analysis when you start getting these engines put in the workflows and so on. So we're starting to get to a different phase where the compute power is there to do this. A lot of the modeling is there to do this, and then we're starting to know what we're starting to know what the right architectures and so on are. And this also can be used as a tool for helping us interpret and understand what's going on. So if we have lots of training data, for example, we can then look at it in terms of latent space. These are just the 3 highest weight dimensions in the latent space. And you can see all these points are different training points that were used, and they actually all clustered together. And they have characteristic ways to connect to each other. Those are phases, and that's telling you if it's a first order or a second order transition that connects them and so on. And you can use these for easily generating out phase diagrams. When you've got these networks trained, of course, you can change from, say, taking an hour to compute what the model would look like in scattering space. It literally does take an hour to calculate these things. And then these neural networks instead can calculate those things in, say, under a second. Right? So they're massively more efficient. And, so these are now being deployed at an early stage in with multiple things like diffraction and this is chemical spectroscopy and then magnetism. But we're really at the start of using this stuff. Now, one thing I want to show now is just ice. This is for the benefit of Roderick to some extent. So we're not chance to look at. But ice itself is actually an incredibly complex material. We're not getting it here, I don't think, but we're certainly going to tomorrow in Tennessee, right? And actually, even very simple things like snowflakes, they don't actually fully understand why snowflakes form the way they do with all these patterns, right? So they're actually massive mysteries in ice. So we've been working with a paradigm of ice for the last 100 years, which is, you know, at least commonizing out your freezer is just an ordered lattice of oxygen. So then the hydrogens aren't, they're disordered, but obey the ice rules. So they've got kind of constraints in them. And well, that's about as much as we know about ice. No one can calculate the couplings in ice yet accurately, but it's essential. If you can't do ice, you can't do water properly, so you can't understand biology properly, right? So these hydro-bodied systems are incredibly important for basic research. So, you know, the kind of question is can we, you know, if we can get our act together, we start deploying more powerful AI. My thesis is that that's coming and we're starting it. And that's going to open right up. And I think it's going to transform at least the scattering science as we get a hold of it. The question is, yeah, if we've got these big data sets and they are potentially, you know, well posed in terms of if you have the right algorithm, you could figure out what's going on. Can we discover something, right? So in other words, would we shift over to discovery based? In other words, would you almost separate the data collection process from the understanding? This is you know, links in with the question of where papers go and what science produces. Does it, you know, it changes what we do. Okay, so we have this huge data set which includes all the diffraction information, all the inelastic information in this vast volume of complexity. So the interest that drove all this was Project and I are very interested in the quantum phase of the hydrogens at super low temperatures, but we need to understand the structure and so on first. Okay, so where did AI come in? So we don't use AI in the final analysis. Where AI came in was it was using all these autoencoders, allowed the rationalization of all the patterns you saw in this very complex scattering space, and allowed the whole problem to be simplified. So the AI was used for simplifying it down to a human level, where actually there were some insights. This is Tennant did this. He did an amazing job on it. It's absolutely brilliant work that he's done. But he used that to figure out an underlying way of looking at all the scattering and the modeling. And he was able to solve this, the dynamics and the structure of ice using this. So what happened from it? Well, small features that we would probably not pay attention to turned out to be super important because they were signatures. It wasn't evident in the diffraction. In the inelastic, it became evident there were what are called Dirac strings. In spin ices, you get things called Dirac strings, which are the long rows of kind of aligned spins that go through the kind of spin ice phase. And ice has them as well. So common ice that you get your freezer has these. And it has them when you just freeze it. And they actually develop and there are more forming as you go down to lower temperatures. And then they kind of freeze further. And there are no more of them. And they're at low enough level that wasn't visible in the heat capacity and in the entropy, which was originally done for ice. So that was a discovery. So ice isn't what we thought it was. It has these other structures in it. And those almost certainly will play a role in snowflake formation, which we will encounter on Saturday. And other kinds of freezing. Right. So okay. So yes, it was possible to take this using sufficient level of technology and actually mine it back. Now there's a lot more in that data than we pulled out. So you can almost say, okay, this data is a resource, and you can mine it given sufficiently sophisticated tools. Yeah. So the data is a thing in itself. The AI is another, and so on. Where's the origin of the partial order? It's actually coming from there's slightly different electrostatic energies associated with the way the molecules sit, and those are actually what a small tipping force that in fact causes this formation. And in fact, this is a non-equilibrium, and you end up with non-equilibrium states as you freeze. Okay, so now I'm going to switch gears into how many minutes is that, Dave?
Let's see. I think we have 17 left.
Okay, so that was the thinking for machine learning. Right, so one impetus for dealing with machine learning was our interest in quantum systems, quantum materials, because quantum materials are really difficult. And quantum materials are really difficult for two reasons, not just one reason. I think there's two reasons. The first reason is that many quantum materials, I'll talk about ruthenium trichloride next, because it is what I classify as a difficult quantum material. I classify it as a seriously difficult quantum material. And I'll explain why in a minute. But many of these quantum materials are complex materials. They have lots of different parameters. They're really complicated Hamiltonians. The second thing is, the physics hasn't been fully worked out yet. I mean, we really don't know how to calculate observables in a lot of cases, except for maybe exact models or some special cases. So we're looking for ways that we can make sense of data and make sense of data, make sense of the physical reality in materials. As I showed you with AI, we're able to reconstruct the atomic scale structure and dynamics using that. So we want to do something similar in these quantum systems, but actually it's much harder. So you're adding to the kind of reality of classical systems, this quantum superposition and so on, factoring in. So in the material ruthenium trichloride, which is one that was mentioned by Gabor earlier, it has Kitaev interactions. The Kitaev interactions are like second-order interactions. The way you get the Kitaev Hamiltonians, you've got to switch off the primary interactions like the Heisenberg interaction by having like 90-degree bonds, cutting off that exchange pathway. So you then can get the Kitaev interaction, but you're going to get all the other grubby little terms there, elevating to actually important. And there's an awful lot of those. So the problem with ruthenium trichloride, which actually shows lots of incredible behavior associated with liquids, is we have great problems understanding it. I'm not going to show you a solution to that today because we're still working on that one. So we like working on the technology for a bit, but the problem is with actually making sense of all these different interactions. But we did do AI on it and do machine learning using the same strategy, just for a 6-parameter model for ruthenium trichloride, which didn't give us a full understanding of it. We have to go up to, we think, a 12-parameter model to actually do this properly, but we got kind of distracted on other problems for a bit. So anyway, this was some work we did with fluid elastic data, figuring out the Hamiltonians using this technology. For doing the simulations, we use semi-classical approaches, but there's a reason why that makes sense. Quantum effects will generally not be captured by a semi-classical method, and so if you train your neural networks on that, they will not be familiar with the other quantum features, and they'll just ignore those, so they won't influence your analysis. Okay, so now I want to talk about what else we can do, and I'm going to introduce now using quantum information ideas, where we could use those for experiment. And instead of doing it on ruthenium trichloride, because it's I'm going to apply these and show you these for a triangular lattice system that we've been working on recently. And this is pertinent to Anderson's resonating valence bond hypothesis. So Phil Anderson stated, I think 1973 or so, that if you had the triangular magnet with spin a half and it was antimagnetic interactions, it would form a quantum state which would look essentially like a superposition of all the different patternings of singlets between spins, and that would be a quantum spin liquid. That doesn't happen for the nearest neighbor Heisenberg model. It actually goes into a 120-degree structure, but if you put actually fairly small next nearest neighbor coupling, you will just destabilize the 120-degree order, and then it's expected to go into the spin liquid. Okay, so actually there's a lot of progress happening in triangular spin-a-half systems, and what we did was we wanted to do, because the spin liquid problem is very hard, we tried to approach it methodically and step through materials so that we understood we were working on things that we knew made sense. So we've looked at these kind of materials like potassium ytterbium diselenide and sodium ytterbium diselenide so that we could systematically change cesium, potassium, and sodium, and so on, to change the properties. So we could work systematically with them. And there's a huge number of triangular materials out there. I won't go into them all, but it's a very truly rich chemistry. So it's the kind of thing that you just go along and say, Dave, give me this, and no, yeah. So, but there are actually vast numbers of them. Right now, I'm going to talk about entanglement. So what we're going to do now is we're going to use entanglement, and I think we're actually going to use it in a useful way to actually make some deductions that turn out to be, I think, quite important in the case of the spin liquids. So entanglement, we can think about entanglement in terms of the measurement of entanglement, really dating back to John Stuart Bell, his proposition. And of course, he had this fantastic insight that you could show that particles were entangled. He used the idea of the photons by doing polarization measurements of independent photons. And then by doing a sum over correlations of the polarizations of these, he constructed a measure, and he made an argument if we're above a certain level in that, it can't be explained classically. I mean, the kind of easy way to think about it is it's kind of like a two-spin generalization of the argument that, well, if I know my spin 1/2 is kind of weird and quantum mechanical because if I measure any spin direction, it gives me 1/2, but I know the spin squared is going to be, root 3 upon 2 or whatever. Right? So it's exactly that. So in a way, it's a kind of generalization to multi-particles of that essential thing that's special about quantum mechanics. So what you would need to do is if you're going to tap quantum correlations and see the correlations in it and expose that, you're going to want to get correlation functions and the correlations between different spins and their different components over space and over time. And so, but with the very large data sets we have that we're getting off these spectrometers, we can readily Fourier transform from wave vector space into real space and also from frequency into time. So that's an essential step that's necessary if you want to start thinking about whether I can measure something and make some deductions about entanglement in it. So how does, the next talk is going to talk about entanglement more, so I'm going to just skip over stuff here, but I'm giving an experimental perspective on how we can think about it in a practical way. But one idea is that so essentially entanglement indices are not unique. There are many different constructions of entanglement indices you can come up with, they're kind of seeing different aspects. The same an order parameter sees a particular aspect of the structure, and you can imagine multiple of these in some hyperspace of entanglement, and then at least by multiple entanglement measurements, you're going to get locating in a meaningful domain. Right? How much time have we got left? 8 minutes. Okay. All right. So there's only really 3 entanglement indices that have been worked out for neutrons, and there's almost certainly loads more. So there's 3 that we bothered using, and actually, there was a lot of work done by Pontus Laurel. I did a fair bit on it. We put a big review article together last year for people's benefit, because we trawled through the literature and found what we thought was every example that had been done and all the entanglement indices that have been proposed. And so we tried to put them all in one place and explain this, but also entangled particle applications as well. So there's the one tangle, which actually for neutron scattering is really easy to get. It's the entanglement between a unit of the system and the rest of the system. It's actually related to the Bragg peak intensity. And from that, you can deduce the amount of entanglement overall in your system, essentially. The occurrence or 2 tangle is basically the equivalent of the Bell's type inequality, which is not very useful in condensed matter, right? Because we have quantum monogamy, as I'll show later. And quantum Fisher information, which is related to metrology, which is basically an integral, a kind of integral in spectroscopy. And that one we can relate to the entanglement depth in a system. Okay, so I won't go into more detail on that, but essentially by taking these measurements, we can use these formulae, and then you can actually start to make some deductions about entanglement content. And for your interest, or lack of interest, here's all the entanglement indices essentially that we proposed for condensed matter today that we could find, our quantum measures, and the experimental probes that can detect them. And these are the materials that have actually got some data on it. Right, so there's actually been a lot of kind of research trying out some of these things, but it's only really very recently that we're putting multiple witnesses together, and quantum Fisher information, I think, is a very significant step for it. Okay, so here's our first triangular magnet, potassium ytterbium diselenide. This is the kind of neutron scattering data. We're not going to explain it in depth, but it's beautiful data. It's a very beautiful 2D system. We get full wave vector energy. Very it's highly quantitative data. So it's super 2D. This system actually orders about 300 millikelvin. So it's not spin liquid, but it orders at a low temperature. So it's near being one. Now here's the witnesses. As I'll show you next, the one tangle, because of the order, will be about 85% of the spin is entangled. 15% is unentangled in the system at lowest temperatures. This is what you get when you try and do the two-tangle, the Bell's inequality. What this line means is whether you witness or not. None of the points are above that line. Right? And there's a reason for that. And that's because of monogamy. In the resonating Valence system, you're going to share these singlets with other singlets, with other sites. And the way these entanglement indices work is you have to have gone above a classical value to see it. And that sharing has diluted the witness level enough that it doesn't work. So that's kind of what you expect for a resonating Valence system liquid. Here's the quantum Fisher information. As you go down in temperature, the entanglement depth's getting bigger and bigger. We don't know how, we didn't measure low enough to know whether this is going even further up. That is 4 farm type entanglement, which I think we're going to hear more about. And that's a lot of entanglement, and it's actually more than RBB is supposed to have. So the entanglement depth suggests that we could be near quantum criticality, boosting the level of entanglement in that. So that's kind of where it starts getting useful, is we're getting some clues from the quantum entanglement. And actually, remarkably, this system is showing omega T scaling. So it shows quantum criticality in omega T scaling, which is pretty unusual in a clean system. This isn't a Harry Fermi system order. This is a 2D quantum magnet. So that's pretty unusual. We have omega T scaling there. And we can get the Hamiltonians out of these materials, because although we're not taking them to full saturation, because the magnet in Oakhurst didn't work properly for a long time, we're restricted to the 1/3 plateau. That's why we did it with this 1/3 plateau. But then you have to use nonlinear spin wave theory or whatever to do that. And Christian Pratisa did that and his group for the fits. So we have, for our different materials, the sodium ytterbium diselenide and potassium ytterbium diselenide, we have the fits. And from these fits, we can extract the Hamiltonian out. So potassium ytterbium diselenide is extremely isotropic. It's very much a nearest neighbor with a little bit of next nearest neighbor, 4%, 4.5% next nearest neighbor coupling in it, and that's it. A really simple Hamiltonian from that measurement. And that puts it here on the proposed phase diagram. So it has the 120-degree order. We see it as it should. It's on this side of the phase diagram, and it's picking up the quantum critical fluctuations. Right? So that's where we localize it. And since we've got the parameters and all the rest of it, it can be compared to the DMRG calculations, to Stringer boson calculations, and it's kind of all matching up to within the ability of the current theory calculations just now. So this is kind of playing out in a nice way. And then I want to talk about the sodium ytterbium diselenide, because the coupling parameters that we get out from the Hamiltonians across here to the quantities for liquid side. Right, so it's just a straight multiplication of the system. And the question is also, is it in a quantum liquid state, or or also what kind of state would it be? So we have the parameters. We can localize where it is on the phase diagram. This is what the scattering looks like. And these are matrix product state calculations from Joel's group. And here's some data. Unfortunately, I didn't make them the right scale. But these are matrix product state things. And it matches well. It also matches very well to a Schrödinger boson calculation that Christian's group did, and his group did. And this is for a Z2 basis. This is for a Z2 spin liquid. So the scattering is matching with what's expected for a Z2 spin liquid. How long left? 2 minutes?
1 minute.
And how many seconds?
33 seconds.
Okay, so so Johannes Knoll has done the calculation for the U1 spin liquid, which doesn't look like our data. So it's suggesting that our sodium atomic diselenide is the Z2 quantum spin liquid line. And there's some calculations that Steve White and Andrew Chernyshев have done, which are showing there's a very large domain with the anisotropy where the spin liquid will still remain stable. XY type or Ising type. So in fact, the domain of stability is really big for the triangular lattices, for the quantum spin liquid, theoretically. Okay, this is just some heat capacity stuff. And then we get into the fact that it's a really difficult system. So we're seeing an anomaly in susceptibility at very low temperatures, which is suggestive potential of a gap. However, working at these really low temperatures with nuclear spins and all the rest of it is really hard. Okay, so that is indicative that something really interesting could be going on. But this is not the kind of temperature scales that energy scales we can really work with neutrons currently well with, and it's also very difficult methodologically. So the rest is making a lot of sense, although I'd say the properties at lowest temperature need work to make sense of. Entanglement, we're seeing no order. So we think the entanglement, one tangle is a complete spin entanglement. Again, no two tangle, but entanglement depth is lower. Now here's where this gives the quantum Fisher information to become useful. Because if I go further towards a critical point, further into the quantum critical fan, my entanglement depth will go up, not down. I have to go through the fan to go down again. So the entanglement depth's gone down here. That indicates we've gone beyond the quantum critical fan, right? So that's a kind of cool thing using a witness. So the witnesses do provide a kind of way of measuring some aspects of criticality as well. So I think it's putting it on this phase diagram round about here. Although what's happening, I've put a dashed line here. When you get down to 40 milli-K, I don't know, right? This is the kind of really hard bit I don't think we're well set up for doing really, really good measurements down here. Yeah, so that's, I'd say that we're hitting serious experimental barriers at this point. Okay, so to finish off, did I do my conclusions?
Yeah, well, it just takes time away from questions.
That's fine.
I think people are wanting to ask questions.
Oh, okay.
I can sense it.
Okay, conclusions. Machine learning. Okay, so it's very, very powerful what machine learning is. You could give us a paradigm shift from hypothesis to data-driven. The capabilities are now deploying. We could be seeing hugely faster materials throughput and so on, data availability and understanding from this. And then one of the questions, where does quantum information fit in? And also, where do all the kind of more quantum calculations, which are far more intensive, how are they going to fit in this world? AI is getting a lot more powerful. The reason we've not been doing this till recently is, when you get to condensed matter applications, this is the development of AI. This is the inflection point where you go to deep learning. Well, the applications I showed you are up here. They take a lot of training data to do. And so, it's more recently that it's really become feasible. So science applications for AI are really difficult. They're not easy. We're not going to get a business anytime soon. very, very far from it. For the spin liquid, so appears the potential set to spin liquid. I think we got a lot of trouble at the lower temperatures. I think we got challenges there. So I don't want to be definitive about that. SFQ and omega entanglement, this is the gap, Hamiltonian. A lot of this is matching together, but you know, you really need that concrete evidence with gaps, I think, for a Z to that. Okay, so the Heisenberg, you know, we've got a really good Heisenberg model, the high accuracy. That's it. That's finished.
Once it goes 109,
Ah,
wasn't 100.
that was
Got
50.
another 50 backup slide.
No, they're actually the templates for the like the dog and stuff at UT, the torch bearer,
There you
that
go.
kind of stuff.
Okay. Questions? Yes.
Yeah, I fully agree with you that the structure factor contains information about entanglement.
Yeah,
But I just want to make sure I understand correctly. The entanglement is a property of the ground state. So therefore, it seems to me that it should connect directly to the equal time structure factor, which is dynamical structure factor integrated over frequency. So I wonder, have you looked at this way?
yes, we have also, but I mean, the problem is when temperature comes in. Yeah, so the problem is with temperature. So, you know what's really needed is some theorems that you can use. So, so you're saying for equal time structure factor, yeah. So the quantum Fisher ratio is really good because if the equal time Cauchy function is the one you need if it's just the ground state, but when you're dealing with thermal states, that's not enough. What the quantum Fisher information does, it allows you to kind of, it does a spectral analysis where it essentially takes out the thermal part. And it, you know, it adjusts for that.
I mean, I guess.
So that makes it,
Right.
yeah.
I guess I find that people talk about all kinds of ways to quantify the amount of entanglement in the,
Yeah.
in the finite temperature. And yeah, I need to think.
Yeah.
Yeah.
So that's one of the nice things about quantum Fisher information is it's really a practical measure that is easy to deploy. What would be great if there was more work done on entanglement that actually generalized the arguments, because there's just not that much there. We're not inventing, we're just using what we can find.
I mean, some of the bounds you quoted, I think, are for the equal time for example.
We have to keep going or else we'll miss it.
Yeah,
Okay. Thank our speaker again.
that's right.